Our weather forecast is based on acquiring weather data from more than 10,000 surface weather stations worldwide, ships and buoys, radio sondes, aircraft, satellite, radar, and more. Data from all over the world are collected by the World Meteorological Organization, and they are forwarded to our National Center for Environmental Prediction, the weather forecast offices, to eventually produce regional forecasts. The forecasts are the result of so-called numerical weather predictions. A numerical weather prediction starts with weather observations. Measured data are used to construct the initial conditions. Computers plot surface and upper air charts from the collected data. Upper air charts are indispensable for numerical weather predictions. Step number 2 is data assimilation. The atmosphere is divided into a series of boxes or grid cells. An interpolation and data initialization creates an evenly spaced, smoothed dataset. And step number 3 is forecast model integration, where mathematical models use equations that describe how atmospheric variables will change over time. The outcomes are so-called progs, or prognostic charts. A variety of forecasting tools help the weather forecaster with his job. Meteograms are forecasting tools that show how weather variables have changed over time. Soundings show vertical profiles of weather data. Thickness charts show the difference in height between two constant pressure levels. They are related to the average air temperatures between these levels. A typical one shows the thickness of the air layer between the 1000 and the 500 millibar levels. A typical problem with the progs is that small disturbances can amplify and lead to huge uncertainties in the forecast. One possible help is an ensemble forecast. These ensemble plots show the outcomes of various computer models. If all models agree, the forecaster will be relatively confident about his forecast. We differentiate between various kinds of forecasts. Persistence forecast assumes that future weather will be the same as present weather. It is often accurate for a time span of several hours, especially in regions which are not strongly affected by the jet stream. Steady state or trend forecasting assumes that a surface weather system such as a cold front will maintain its speed and direction. The pattern recognition method assumes that existing features on a weather chart will produce similar weather patterns as they have in the past. The probability forecast is used to determine the likelihood of certain events, such as White Christmas, based on at least 30 years of data. The climatological forecast refers to forecasts that are based on average weather, or the climatology. Long-term averages are taken as a good guess for the weather on a certain day. We also differentiate various types of forecasts. The nowcast is a very short-range forecast, typically for less than 6 hours. It's based on an interpretation of surface observations, satellite and radar images. It's typically based on the steady state method. The short-range forecast aims at a period from 6 hours to 2.5 days. The medium-range forecast, from 3 days to 8.5 days, is mainly based on progs. And finally, the long-range forecast or outlook for more than 8.5 days. For this period, progs are inaccurate and forecasts are mainly based on the expected average weather. Input can be projected upper air lows, persistence statistics, and other means to estimate future weather. If you do a forecast that is based on surface charts, there are 4 rules that can help you. For short time intervals, you can assume that systems, such as high pressure or low pressure systems, maintain direction and speed. A slightly more accurate approach would assume that low pressure systems move in direction parallel to isobars in the warm sector. Rule number 3 states that lows move to the area of the greatest pressure drop, or highs would move to the area of greatest pressure rise. For this forecast, it would be useful to have a map with isobars, which are lines of equal pressure change. There are some signs you can look out for if you want to predict the weather from local observations. If winds start blowing from south or southwest, clouds building to the west, it is warm or hot and humid, and you see the pressure is falling, then these might be indicators for an approaching cold front with thunderstorms. So your local weather forecast would be to predict showers, to predict it's turning colder and windy. If it is relatively cool, surface winds come from east or southeast. You see high clouds, maybe with a halo, that are thickening and lowering. The pressure is falling. Then this might be an indicator for an approaching warm front. And your local weather forecast would predict precipitation in 12 to 24 hours, rain and possible thunderstorms in summer, or snow changing to sleet or rain in winter. Have you ever observed clouds moving in different directions at different altitudes? This is also a good indicator for weather phenomena. If winds change direction with altitude in a clockwise sense, then we speak of veering winds. If winds change direction with altitude in a counterclockwise sense, we speak of backing winds. Veering winds typically occur ahead of a warm front. In winter, that could mean we have warm advection, possibly snow changing to rain. In summer, it could mean rainfall, possibly thunderstorms. Backing winds typically occur behind a cold front. That means cold advection, possibly rain changing to snow in winter, and generally colder conditions. Here is an example of how a meteorologist might make a prediction. It is Sunday, March 25th, 4 p.m. in San Francisco. The meteorologist on duty observes barometric pressure of 1016 millibar, which is slowly falling. The surface map gives no clues at this time. There is no approaching front, only a stationary front over the Rockies. There is a weak low pressure system 700 miles west. It has been there for days. He looks at the 500 millibar chart. He sees that the 5,640 meter height line is located over California, and he knows from his experience that this refers to a high statistical probability for rainfall. West of San Francisco, he notices strong meridional wind flow, a high pressure system and 2 troughs. This system is called an omega high, and he knows that this is a blocking high that tends to persist. A closer look at the trough reveals closely spaced isobars, meaning stronger winds in the west and northwest, and widely spaced isobars in the east. Based on his experience, he concludes that this trough will deepen. West of the trough, he sees winds blowing across the isotherms. This is called cold advection. The meteorologist also notices a minor undulation in the upper airflow. This is a shortwave trough that is moving southward. Again, he knows from experience that these 3 factors, cold advection in the west, warm advection in the east, and the shortwave trough, will lead to a deepening of the trough. A deepening upper air low pressure center can be favorable for the development of a surface storm system. The question is, where will upper air divergence form, which is necessary for surface convergence? The vorticity maximum is in the region of the short wave. Upper air divergence is east of the short wave. That is where the storm can develop. As a next step, he needs to look at the computer progs. The progs of the different computer models show generally good agreement. The upper air trough moves eastward but stays off the coast. Model A and C move the trough and the short wave eastward a bit more quickly than B. From experience, the meteorologist has less confidence in the Model B regarding upper air troughs. Therefore, he concludes that the short wave will approach the California coast at 4 a.m. on Monday morning. The upper air low will remain off the coast. Southwest winds will pump moisture into the region. A series of short waves will bring rain through Tuesday morning. So his forecast is increasing cloudiness Sunday night with rain beginning Monday morning, periods of rain likely through Tuesday morning. Here is what happened in reality. The reality shows good agreement with the progs. The trough and the surface low, now down to 1004 millibar, have deepened. Now he takes more information from the satellite pictures. The infrared satellite image reveals that the middle clouds over California will be displaced by cumulus clouds. The comma clouds point towards the development of a mature mid-latitude cyclone. Cumulus congestus developed near the second short wave. Consecutive satellite images provide information when the clouds will reach California. The leading edge of the comma cloud is just offshore on Monday afternoon. We will expect increasing rainfall. His amended forecast reads, rain beginning this morning, becoming heavy by this afternoon, strong and gusty southerly winds. So what is next? On Monday afternoon, we see that the mid-latitude cyclone has strengthened and moved closer to the coast. The cold front marks the position of the comma-shaped clouds. The front is the result of cold advection in the west and warm advection in the east of the system. On Tuesday morning, we notice that the front moves onshore. It is accompanied by heavy rain and gusts. The storm system has deepened. Its center has now 998 millibar. The next short wave is approaching. Will it cause the next series of thunderstorms? Also, will the storm system that's off the coast deepen or fill? These are the next questions that the meteorologist will have to answer.